Please take seats because we will begin the last part of the fourth session about continental drift and paleoclimates. And we have the pleasure to welcome Bärbel Hönisch, who is a professor at Columbia University and works at Lamont Doherty Earth Observatory. And we will speak about atmospheric CO2, then and now. What can we learn from the past? Thank you.
Thank you so much. Thank you so much again for having me here. It's been really a pleasure to come to Paris and also to learn from all of you. I have to admit, I'm a paleoceanographer. You will see I reconstruct climate change from ocean sediments. I've literally been feeling a little bit like a fish out of water here. And so when I first got the invitation and I heard about Xavier Le Pichon, I have to admit that I didn't know about him because he had returned to France long before I arrived at Lamont. And so I had to do some research. And the research that I did is, first of all, I landed in Bill Ryan's office, and Bill Ryan was a very good friend of Xavier Le Pichon, and he told me a lot of things about him, and he also introduced me to this paper that we have seen several times by now. So reading that was a really nice transition through the history of Lamont and also to his introduction to science. So we've seen a lot of pictures of him. I was looking for one on the Vima. This is the Vima on the front left. When Xavier Le Pichon first came to Lamont, he came on a Fulbright stipend. He came directly after his undergraduate studies, and he, as we heard earlier, he actually served as a physical oceanographer on a geoscience cruise, and that is the cruise track down there. We've heard a lot about it. What we didn't hear about is that his career could have ended right there on that cruise because the Vima actually ran into a typhoon and the ship was almost lost during that cruise. They all made it back, and thanks to that we have a lot of information about plate tectonics right now. But when he started studying at Lamont and in France, and then later on came back to Lamont, it was really a pioneering time in plate tectonics and in seismology. So what the director of Lamont had just realized at that time is two very important things. One of them was that the oceanic crust is much thinner than the continental crust, and the thickness of the sediments on top of that are actually so thin that they do not agree with the age of the continents. And that was an indication in itself that the seafloor was much younger than the land. Than the land is. And that, of course, was later on complemented by the geomagnetic striping of the seafloor that then led to this evaluation of the plate tectonics theory and how these continents were moving across the planet. Now, all of this information has also important consequences for me. I'm reconstructing paleo CO2 from ocean sediments. And of course, we will learn more about that in Dan's talk, as we've learned already that plate tectonics are very much related to the evolution of carbon dioxide, what's coming out of volcanic eruptions, and then also what is being consumed by weathering. A very other practical part of that for me is that I need to know where my sediment cores are, because depending on where they're located, that actually tells me whether they're suitable for the reconstruction that I want to do. And so here's just some indication of sediment cores or different records that we have used for paleo CO2 reconstruction. These are all these different dots. And this is a timeline. So this is where they are today. If you're going back to the Oligocene 26 million years ago, you see they're in very different locations. And then we're going back to the Paleocene, they're again in very different locations. And that is important for me to know to find out where these reconstructions are actually suitable. Now, I don't want to go further into that. I want to go back to this question, basically to the beginning of the motivation for this talk, and that is that we have been observing that carbon dioxide in the atmosphere is increasing steadily. I just checked the data for today, so we're now at 430 parts per million this year. That's not the average. I think the average is now 429. But they are increasing steadily, and we're seeing this. These are the CO2 measurements that started in 1958 on Mauna Loa, and we're comparing them to the temperature anomaly since 1880. And you can see there's a very nice correlation between the carbon dioxide increase and the temperature increase on the planet. Of course, there was a reason why they started doing these analyses. They already had the idea that the carbon dioxide was increasing, but they didn't really know what the point of reference was. They didn't know what to compare it to. And that information had to wait until pretty much the 1990s, when the more reliable ice core records were coming out, of the more highly resolved ice core records. And those records showed very clearly that over 800,000 years, those are the longest records that we have right now, the carbon dioxide concentrations were going up and down approximately every 100,000 years. And they were never any higher than about 280 to a maximum of 300 parts per million. Thanks to our human actions, we've now increased this to 430 parts per million, as I mentioned before. And in the future, the expectations are that it might be as high as maybe even 1,000 parts per million. That worst case scenario is probably not quite as likely anymore right now, but we're on a trajectory to keep increasing that carbon dioxide pretty substantially. And because of that, the temperature on the planet will also keep increasing. So global warming, we've heard a lot about. We've seen all these scenarios that are outplaying already, whether it's droughts, whether it's wildfires, more storms, more rain, the ice melt. In the ocean, we have the other CO2 problem, and that is the ocean acidification. So when the carbon dioxide is dissolving in seawater, that it actually reacts with the seawater and turns into an acid, and that has consequences for marine life that now have a harder time to build their shells and their skeletons. So knowing all of this, we want to know how bad it's going to get, what the consequences are going to be in the future. And of course, we don't know the future yet, and so we can go back into Earth history. And for doing that, we cannot use any direct measurements anymore. With the ice core measurements are really our gold standard. So if we go back to this picture over here, the ice cores, they're basically snow that falls on Antarctica, and at some point it compacts, and it includes bubbles of ancient air in the ice. And those bubbles you can see in this slice of ice. So this is an ice core. This is a slice of that, and all these little dots in there, those are old. Those are enclosed bubbles of ancient air. So it's a direct archive, and that is fantastic. And hopefully, maybe by the end of this year or early next year, we will extend this record to 1.5 million years. The record is already there; it just hasn't been published yet, and we're all eagerly awaiting how the data look like. But that might be the extent of what we can get from the ice cores, because there's not much more ice available that is pristine and that can be analyzed. And so for learning more about the geological record, and we've seen some records of this already, there are some really interesting climate transitions that have supposedly been associated with carbon dioxide variations. And so in order to estimate that, we have to go back to proxies. And proxies are not the real thing. We're not measuring actual air, but we're measuring something that is related to the carbon dioxide in the atmosphere. And these are 8 different proxy groups that are fairly well established. All of these have been used for reconstructing carbon dioxide from the atmosphere. These ones over here, so these are represents the alkanones, so they're biomarkers that are produced by algae or the foraminifera. Those are marine proxies. All these other ones here are terrestrial proxies. Most of them are based on either kind of vegetation or on minerals that are precipitating in soils or in different other reservoirs. To explain how these proxies work, we don't have enough time for that to go into every single one of these, but the simplest one to explain is actually the stomatal frequency proxy. Stomata are breathing cells, so here's a picture of one of those. So they're breathing cells that plants have, because as they're photosynthesizing, they need to open up these cells to let the carbon dioxide in. But as they're doing that, they're also running the risk of losing water to the atmosphere. So they try to balance this, carbon dioxide in and water out. And so when you look at these calibrations, so here, the way how you can calibrate them, you can use herbarium data, where you use leaves from herbaria, and you compare the number of these breathing cells to the carbon dioxide concentrations at the time when these leaves were collected. And then when you're taking that calibration into the paleo record, you can count the number of stomatal cells in the fossil leaves, and from that you can then calculate what the carbon dioxide concentration at that time would have been. So if they have fewer, if the carbon dioxide concentration in the past was much higher, they need fewer cells to let that carbon dioxide in, because with every single breath they'd get a lot more carbon dioxide. It's also warmer at that time, and so they would lose a lot more water, and so that it helps them to have fewer of these breathing cells. This is, as I said, the easiest proxy to understand. It's maybe not the most reliable of all of them, but I don't have time to go into all of these other ones. I'm also not an expert in all of these different proxies. And so when we tried to use all of these different proxies, I had to invite a lot of different experts that actually knew what they were talking about. So since 2016, we've had this consortium of experts that work on these different proxies. And we started out with various different workshops where we talked about what we actually wanted to do, how we could do this better, how we could assess our data that we had, and maybe improve our records. And very early on, we decided we wanted to create a database. And so here's the database of all the different records that were published over the last 70 million years. And all of these different dots over there, those are the different proxies that we have been applying. So this is the data archive, and you can see that this data archive was pretty much all over the place. There are also some data that basically said, well, it's sort of higher than this or lower than that. Many of these data were not associated with any uncertainty estimates and so forth. And so we brought all these proxy experts together, and first of all, we documented all of these data in great detail with all the different raw data that go into that. And then we asked these experts, okay, which of these records are actually reliable today? Because we have learned some of these records were collected in the 70s, 80s. We've learned a lot about these different proxies over time. Very often we've learned that we need to process these samples in a different way. We need to clean them in a different way. We need to make sure that we don't mix different species. There are a lot of different things that we have learned about them. And so some of these records were actually sorted out and said, well, these are not exactly reliable anymore. And others were recalculated based on the most modern proxy theory. And so from that, we went to our expert-vetted data product, and this is how that looks like now. So we have a much more constrained carbon dioxide history over the Cenozoic. If you just look at these curves, so this goes to 3,500 parts per million. Actually, this is the same scale for that. But you see that this is much better constrained over here. It's also much more reliant on marine proxies. So the orange and the red data points here, those are based on phytoplankton and boron isotopes. That is not, I do happen to work on boron isotopes, so I like to see that, but at the same time, I don't like to see that, because really, when we're working on these proxies and they're 60 million years old or even older than that, there's a lot of uncertainty that creeps in the older it gets. And so we really want to have a good overview from different proxies, and if they all tell us the same thing, then we can be more confident in that these reconstructions are actually reliable. But overall, we see a pretty consistent picture with the carbon dioxide and with climate. So here's a compilation of the data with different climate data. Time goes, again, from left to right. So this is 70 million years ago to the present. Up here, this is our carbon dioxide record. So the individual dots are the ones that you saw before. The solid line here is actually a model-interpreted line of these data that is somewhat more averaging over the individual data points. But we look at this curve over here relative to the temperature of the global mean surface temperature of the planet, and we see a pretty good correlation there. When the carbon dioxide was high, the temperature was high, and the carbon dioxide was decreasing over time, and so was the temperature. At the same time, this is the sea level. So sea level was much higher in the past when we didn't have any ice on Antarctica. These little globes over here, they indicate how much ice we had. We're always looking at the North Pole and the South Pole. And 50 million years ago, there was no continental ice in either one of those hemispheres. And so sea level was about 70 meters higher than today. We already learned earlier, 34 million years ago, that's when Antarctica started establishing a continent-wide permanent ice sheet. That's when sea level dropped by about 70 meters. And then since about 3 million years ago, 4 million years ago, we now also have ice on Greenland, and this is the last ice age, so the much larger, so the Greenland is just there, this is the much larger ice sheet of the last ice age, and this is where we are right now when only Greenland is glaciated. At the same time, so we have lots of indication that climate is going together with the carbon dioxide, so that's confirming that this seems to be reasonable. At the same time, we're also seeing changes with the evolution of plants on the planet. So this indication over here is, this little green bar over there is indicating the onset of or the diversification of C4 plants. So C4 plants are plants that have a carbon concentrating mechanism. So they evolved at a time when the CO2 was low. You can also see how the vegetation changed from more tree-like to more shrub-like and grass-like vegetation. And then, of course, the fauna went with that as the vegetation changed. So when we're looking at these and we're trying to understand what this all means, here the same data again. This is the CO2 curve. It's now on a log scale over here. The time is also on a log scale, and the color bars in the back, that's the temperature. So we have, and this is all relative to today. So -3 degrees for the last glacial, and then we have much warmer conditions when we're going into the Eocene, warmer by about 14 degrees Celsius. So much warmer climate at that time, and we've seen in the talk before the uplift of the Himalayas somewhere around 50 million years ago, as a suggestion of what might have caused this decrease in the carbon dioxide. Whether or not that's true remains to be seen. But the Eocene optimum, that coincided with the volcanism that associated with the North Atlantic igneous province. So a huge amount of volcanism that released a lot of carbon dioxide. When we're looking at the Miocene, that's the volcanism. Volcanism at that time was more globally distributed, but the Columbia River Basalt region from Colorado to Idaho was also a huge region of carbon dioxide. So this is always interesting to see. The climate skeptic then usually comes, okay, so you're telling us carbon dioxide is a problem, but really right now we're at the lowest part of carbon dioxide in our Earth history. Why do we care? Why is this important? And obviously carbon dioxide has been much higher in the past. And that, of course, is true. But what is also true is that hominins only evolved 7 million years ago, and Homo sapiens has only been around for 300,000 years. So that means that humans have evolved in this cold climate that we know today. And we have developed our infrastructure for these cool climates that we know today, for this low sea level that we're knowing today. And so that doesn't mean that we're actually equipped to deal with conditions that we might see if we go back to the climate of 50 million years ago. Now, Emmanuel has already pointed out this event over here. This is a very interesting one. So this is the Paleocene-Eocene thermal maximum. 56 million years ago, this was an event when paleoceanographers first did some analyses on that, and they found these really weird, bizarre differences in the carbon isotopes and the oxygen isotopes. They thought their mass spectrometers were broken, or they thought there was something contaminated going on with their samples. And so they measured it again. They measured it on different instruments. They measured it in different sediment cores. They measured it on land. And in the end, it turned out that this was an event that was global in scale, and it was actually reproduced in all these different locations. So it looks like it's this really rapid event that is very, very interesting for various different reasons. And one of the most important reasons there is that it's associated with massive calcium carbonate dissolution in the ocean, and also very large changes in the ecosystem at that time. So this is how the world looked like 56 million years ago. These are pictures of sediment cores that were taken on Walvis Ridge, which is off the coast of Namibia down here. And what these sediment cores are showing you is that time goes from the bottom to the top. So this is young and this is old. And this brown layer over there, that is always the onset of the PETM in these sediment cores. And what you see is, first of all, it's light-colored sediment. Those are calcium carbonate. Then it goes dark brown. Those are clay particles. And then it goes white again. And what this indicates is that when you look at this blue line next to it, this is the calcium carbonate concentration in the sediments. It goes from nearly 100% to 0 to then slowly recovering again. So the calcium carbonate in the ocean was dissolved at that time. These are 4 different cores. These are the water depth where they're located today, 2,700 to 4,700 meters. At the time, they were much shallower thanks to plate tectonics. So the shallowest core was actually only 1,500 meters deep. And the deepest core was about 3,700 meters deep. And so to get complete dissolution of the calcium carbonate at 1,500 meters, that was a big event. There was an indication that a huge amount of carbon dioxide was put into the system. This picture here is from a sediment core that was taken from the Pacific Ocean, same time. Again, we're looking at this event 55, 56 million years ago. This brown layer here is the clay layer. Time is going up. We have calcium carbonate here at the bottom, and then later on the calcium carbonate is coming back. And these pictures here, those are discrete pictures from before the event, directly after the event, and then sometime later after the event. And this won't mean very much for you. These are planktic foraminifera. These are the organisms that we're doing a lot of reconstructions on. But what you can very easily see is that these ones are larger than those ones. And what you cannot very easily see is that these are different species than those ones and those ones. So this is an indication that at the time of the PETM, there was dwarfism, there was extinction, there were species that just showed up during this transition period, and then afterwards there was evolution and there were new species that were coming in. So this is an indication that yes, there was carbon dioxide put into the system that suggested acidification, and this acidification had consequences for marine life. And the foraminifera, they're the plankton organisms, so they're at the bottom of the food chain, and so you can basically infer that there were also extinction happening higher up in the food chain. So we wanted to know how much carbon dioxide was there and how much acidification was actually happening at that time. And so we've done a lot of reconstructions. This is now a compilation that was ultimately combined by Dustin Harper 2 years ago. What we're looking at over here is a timeline from 59 million years ago to 53 million years ago. And you're looking at various different marine proxies. So here's the Paleocene and the Eocene. This is the PETM over here. So this is this large event that we were looking at. And the PETM stands out as a very large negative excursion of carbon isotopes. And that is an indication that there was some carbon put into a system from a dormant reservoir. You see that over this time interval from 59 to 53 million years ago, there were other negative excursions over here. And those negative excursions go together with increases in the magnesium-calcium ratio here, and also with decreases in the oxygen isotopes. Both of these proxies give indications for temperature. So increasing magnesium-calcium means that there was warming happening, and the decrease in the oxygen isotopes is an indication for warming as well. And so we measure boron isotopes for this record, and here are the boron isotopes. And you can already see one of the big problems that we're having there. It's much, much easier to measure magnesium, calcium, and oxygen isotopes. They're much more rapid analyses than to make boron isotope measurements. But what you can see is that with these events where we saw warming and carbon isotope changes, we also see decreases in the boron isotopes. And that in itself, without going into any quantitative data, is an indication for acidification already. So we could use we have all kinds of calibrations for this proxy. Some of them were produced in laboratories, and that is something that we're taking into account. But as you see, the data density here is very different from the data density that we have in some of these other records. And so what Dustin did, and that was different from earlier publications of these data, he developed a so-called forward proxy system model. And what a forward proxy system model is that it uses information from an environmental model, from some Earth system model, for instance, and practically models a proxy value. And then you can compare that proxy value to the actual measured proxy values, and you can see how similar or how dissimilar they are. And the more similar they are, the more reliable they become. But basically, from this environmental model, you model all these different processes that we know are involved in developing this proxy signal. So typically, we would go the other way around. Typically, we would use our proxy signal, and we would infer we would make all these assumptions here, and then we would reconstruct what the pH is and what the CO2 was at that time. In these proxy forward system models, you basically say, okay, we think we have some idea of how the system looked like, and then we use those data to model these proxy values. And so in that process, you get all of these different data. You get the CO2 estimates, you get the pH, you might even get the dissolved inorganic carbon, for which we don't have a proxy value. So it's actually a really, really cool way of doing this. And this is a Bayesian hierarchical model. So you basically go through it over and over and over again until your posterior is actually much better constrained than the prior that you put in there from this Earth system model. And so this allows us to go from these data over here to something that looks like that. So we now have a very low resolution boron isotope record that allows us to get very highly resolved CO2 estimates and pH estimates. And so here's again our record from 59 million years ago to 53 million years ago. Here's our acidification signal that we have combined from various different records. There is the CO2 signal that is associated with that. So acidification was on the order of about 0.3 pH units. We have warming from our sea surface temperature proxies that tell us warming at that time was on the order of 5 to 9 degrees. The acidification is similar to what we're expecting by the end of this century when we keep burning carbon dioxide. We've seen that there were ecosystem changes in the plankton. What we don't really appreciate yet is that the onset of the duration, we see this very rapid event that comes and goes, but to go into this event, that took about 3,000 to 5,000 years. So much, much longer than what we're doing today. And that means that the pH change is on the order of 0.01 units per century. Right now, we're decreasing our pH by 0.1 units per century. So this event was about 10 times slower compared to what we're doing today. And the other really remarkable point here is that in order to get out of this event, to neutralize out of this carbon dioxide, that took 150,000 years. So 150,000 years, if you divide that by 25 to think about how many generations of people that is, that means 6,000 generations of people. That's a very, very long time. So this is just to put this into comparison. These are the ice core records here. This is atmospheric CO2. 300,000 years before our time, we see these carbon dioxide values going up and down. This is when the Neanderthals died out. 40,000 years ago, so that's just 1,600 generations of people. And now here we have our CO2 scenarios. Maybe this 8.5 scenario is not so likely anymore, but this RCP 6.0 scenario going up to about 900 parts per million is not that far off from where we're going. But if you look into how long it takes to recover from that, that's a very, very long time. So practically from what we're doing today, that carbon dioxide that we're putting into the atmosphere today, without doing anything else to it, without sequestering any carbon dioxide, will actually practically stay with us forever. Why is that the case? It's the case because these processes that neutralize carbon dioxide naturally are taking a very, very long time. So the first step that's happening for carbon dioxide is that the carbon dioxide dissolves in seawater and then gets moved through the ocean with ocean circulation. That takes on the order of hundreds to maybe a couple of thousands of years, and it dissolves away some of these calcium carbonate sediments at the seafloor. So that is the first step in the neutralization. But the much longer step in the neutralization is this weathering reaction that we have heard about in the previous talk. It takes a really long time for that to happen. So we're talking on the order of 10,000 to hundreds of thousands of years. So that kind of tells us where we are in this process. To think again about where we are today. So this you've seen this figure before. This is sort of the extent of where we might be in the future. So if you think back about where this might bring us to something on the order of the middle Eocene to maybe the beginning of the Eocene, there was a much, much warmer climate. Of course, that doesn't mean that climate will change in these dramatic terms on very short timescales, not in the order of decades, not on the order of centuries, but we're heading in that direction. And we're heading in that direction at a rapid pace. It took Earth tens of millions of years to neutralize all this carbon dioxide, and we're putting it back into the system just over the course of a couple of hundreds of years. So we are actually in the process of extending this record, and I know many of you would like to see those records, but we're not quite there yet. So what we have published so far is the Cenozoic record, so the last 65 million years. We're now working on the entire Phanerozoic, so there are other records that have been published over the last 430 million years. That's the earliest record that we have. And here again, we have a new consortium of scientists, of experts who have come together to try and work on this. And this is now coming together. So at this point, we have almost completed the archive for all of these records. So there's a total of 320 records in there. I think we still have to work on another 15 or so until we have that complete. This is now being led by Isabel Montañez. What we're doing different in this record is that we're not actually sorting out the records that are not as reliable anymore. Some of them will probably sort it out because we can't salvage them. But basically, for every single one of these proxies that exists in here, Dustin Harper and Gabe Bowen are currently producing these proxy forward system models. And so we're going to combine all of those models in a combined curve for that Phanerozoic. That will probably come out in pieces just because it's a lot of work. But this is something that hopefully you will get to see in the next couple of, maybe next year will be the first ones. So that brings me to the end. So what we have is the paleoreconstructions that we have. They do show us that that the concerns that we have about modern climate change, they have also existed in the past. We should always appreciate that our human civilizations have really only evolved in an unusually cold climate. So this argument, it was warmer before, CO2 was higher in the past, that's not really an argument because we are not equipped to deal with those conditions. We also see that this PUTM is probably the closest analog that we have to modern climate change, even though it was 10 times slower compared to what we had. But it did cause massive warming and these ecosystem changes, and it took 150,000 years to get out of that event. And so today the CO2 is rising 10 times faster than it did at the PUTM. And so really we're racing back. We're reversing 50 million years of climate change just over the course of 200 years. Now you might ask yourself, why is she showing us another ship? You've seen this ship before because this ship was formerly known as the Vima. She's now called the SV Mendeley, and she's currently being overhauled entirely. And if you ever want to sail on the ship that Xavier Le Pichon sailed on, you will soon be able to do that because I think she's supposed to start sailing the Caribbean sometime this year. Tickets are not on sale yet, but you might be able to do that. So thank you for your attention.